And we start. All right, we're going to start. Welcome to the Alkebalon Math or Communiversity Math Series. And Communiversity, right, is a community university. Makes sense, right? All right, so what we're going to do is we're going to do Ethiopian math. It's the coolest thing in the world, believe it or not. All right, and so my name is Whitfield, and my number is 561-427-8495. If you have any questions, just give me a call. All right, so Ethiopian math. What's real cool about this is that the ancient Ethiopians, right? Of course, we had the villages and all that kind of stuff, and we have the elders in the villages, right? That if you have a problem, you go to the elders and you ask them if you're not sure, right? We didn't have the internet back then, right? So the elders are wise. That's why they're elders and not olders, right? Because a lot of people are old, but not very wise. We call them olders. So, anyways, what they would do is, if I'm a farmer and I got 9 goats, and I want to sell them for $7 a piece, right? Let's just say, if I can't, because I got no calculator, I can't really figure it out, I could go to the elders, and the elders would do this process in the sand and, come up with the answer, and we know what this is, right? Mm-hmm. What is it?
63.
63, right? So we know this, right, because we memorized it. But this process that the elders would use is quite interesting. Ethiopian math. Here we go. You ready? Mm-hmm. All right. So what happened is that, think of this as a column, right? And this is a column as well, right? And then we're going to think of rows as well, right? So in this column, you're going to have the number in this column, right? And this is how cool it was, is that you throw away any remainder or any decimal, any extra, you just throw it away, right? Other than a whole number. All right. So half of 9 is what?
4.5.
4.5, but we don't care nothing about the 0.5, so we're going to toss it. So it says what?
4.
All right. Now this one, right, all we're going to do is double. Double this column, right? So we half this column and toss any remainder, right, or any decimal, and then we double this column, right? 14. We're there. Half this column again. 2. Right? Half it again. Right? If you half it again, you get 0.5, and you're going to have to toss it, so it doesn't make sense to half it. We stop there. Well, we double this guy as what? Double it? 56, right? All right. So we got the setup now. So what the elders would say is that in this column right here, right, the even numbers are evil. The even numbers are evil. So you identify the even numbers in this column right here, right? And then you cross out the rows that they're in. Right? Cross out the rows that the even numbers, the evil numbers are in. And then what's left in this column, you just add them up. And you get your answer. And it works every time. Right? How cool is that? All right. Yeah. A lot of people first time they see this, they go, oh, that's a lot of stuff, man.
Yes.
It's a long process, but really it's not. It's pretty cool. Check it out. All right, so let's say we're doing 16, right? 16, right? Pick a number from 1 to 10.
5.
5 is a good number. I like 5 too. All right, so 16 times 5. Remember, we're going to go through the process. We're going to half this column, and we're going to double this column, right? All right, so let's do it. Let's get to it. All right, so this is 8. 4. All right? 2. 1. Outstanding. Sounds like everybody's been paying attention. All right, we're going to double this one. What is it?
10.
15.
20, we're doubling.
Oh, yeah.
20, 40,
40,
80.
80. All right. Now, in this column, all the even numbers are evil, right? So we got an even number here, an even number here, an even number here, and an even number there. And what do we do with the evil number rows? We get rid of them, right? And then what's left over in this column is the answer, right? Or you add them up, right? And in this case, it's just one of them. So 16 times 5, without me even calculating anything, right, is 80.
But you say you add those two, right? 5 plus 80? Or
No.
Oh, you don't add
You
that.
cross it out.
Oh, okay. So the
Yeah.
answer is just at the bottom right there?
Yeah. Now, how cool is that? Now, see, it's real interesting, right? Because we're all about, and math is all about pattern recognition, right? Nature is all about patterns as well. So what happened is that it really didn't matter what number you gave me.
Right.
It really didn't. All I would have to do to get any number times 16, all I have to do is double that number 4 times and I get the answer. How cool is that? Right? Because 16 is not going to change its pattern. It's going to be 8, 4, 2, 1. So you're always going to cross out those numbers, right? And the last one is going to be the answer all the time, right? So all you got to do is double it once, twice, 3 times, 4 times.
Yeah, I might need to write that down.
And you got the answer, all right? So, are we convinced that that's cool?
Yes.
Yeah, all right. Now, let's take it.
Let me borrow one of them pens.
Let's take it one step further. All right, see if you guys really understand. All right? Suppose it was 32 times some number. What difference would it make? Would it make a difference?
No. Because then you just half that and double that. So.
Right. But can you see anything?
Yes, 16 plus 16 is 32.
This would have been one more step. Right? So you would still have this pattern here, but one more step to double. So you instead of doubling it 4 times, you would double it one more time, right? 5 times to get the answer. Do you understand? So 32 times 5 would be what?
Add one more. 160.
Right. You double 80 and you get it. Got it?
I missed that one.
Okay.
Right.
All right. No, that's okay. All right. What happened is that I said, what if it was, instead of 16, 32?
Oh, okay.
Right? 32. See, half of 32 is 16. Half of 16 is 8. Half of 8, 4. Half of 4, 2. So the only difference would be that you would have this 32 up top. This would have the same pattern.
Oh, I got you. Okay.
Right? And then this would have the same pattern. You know,
Half of 5, yeah.
this would
I
be
mean, half.
this would be 5, this would be 10, so this would be shifted up.
Okay.
See what I'm saying? It would be shifted up, and then, so this would be here,
Okay.
all right? So all you would be doing is adding one more double, right?
Okay.
But you cross out everything, and you get to 160. And that's what I mean. So you see, there's a pattern in there. If you use this method, you could get to the answer quickly. All right?
So it's
By
the
process.
same thing as if whatever you do to one side, you do the other. Since you added
That's a
32,
good.
then you have to double it at the end because you added 32, which is 6 times 2. So whatever you do to the left, you have to do to the right. But instead of making it half, then you double it. Is that the same concept?
Kind of, sort of. Here's the reason why it works is because of the concept that you're talking about. Is that the reason why you half this column and double this column and still end up with the answer is because, see, that if you half something, right, then if you double it, you get it back.
Yeah.
Right? And so that's why you're not really affecting the math, you know, by halving this and doubling that. All right? So, you're really getting it back. So, that's in a nutshell what Ethiopian math is, the process. Now, here's the thing. You know, we know that it works, right? We know that there's some patterns that are really interesting that could get us to, you know, answers quickly. But the question now becomes, why does it work? And if you look all over the internet, you'll find people that say that this is magic, right? And as much as I love to believe that our people are magical, and they are, right? And brilliant, right? There's a reason why we did this, right? Because Ethiopia is in Africa, and African, you know, we're Africans, right? And so our people, you know, came up with this process through a logical means, right? And so here's the thing. What's really cool is that, what I didn't tell you, is that I'm actually an engineer, right? So I went to engineering school, right? And there's a lot of stuff that I did in engineering school that most people that has never been to engineering school will never learn, right? And so one of the things here is, you know, forget the 32 for now, right? We started with 16, all right? What happened is there's something called the binary number system that the computer uses. That's what the computer uses. So the computer doesn't understand anything else but binary. So when you put something in the computer, you type it on the keyboard, the computer automatically, instantaneously turns that into a binary code and then manipulates it, right? And then at the end, we'll put out something, light some lights on the LEDs so that you could understand what the computer did, right? What the end product is. So all the underlying calculations the computer does, it's done in binary, right? The computing is done in binary, and binary is 2, right? The prefix bi is 2. Now, here's the thing. Our number system is a decimal number system. Our number system is base 10, right? So binary is base 2, right? Like you said, bi prefix. Deci is 10, right? And so the decimal number system is base 10. Well, the decimal number system is comprised of these numbers here. Just those numbers, right? Those 10 numbers, right? A lot of people think that's 1 to 10, but it's not. It's 0 to 9, right? That's a decimal number system in a nutshell. Every other number in the decimal number system is some combination of these numbers. Pick a number.
10, 1, 0.
Number above 100, like, you know, 100.
105.
105. 105. I like it. Right? The 0 is there, the 1 is there, and the 5 is there. Right? So it's some combination of these 10 numbers. Right? That's our decimal number system. Well, here's the thing. Binary number system is base 2, right? Base 2. The decimal number system is base 10, right? So base 10 is 0 to 9. Base 2 is 0 and 1. Just those two numbers, right? So 0 to 1, right? So if it was base 5, it would be 0, 1, 2, 3, 4, right?
If it was base 5?
Yeah.
Because you
Oh,
start
because
with
you gotta
0.
keep that 0.
Yeah, 0, 1, 2, 3, 4, right? That's 5 numbers. Base 10, 0 to 9. Base 2, 0 to 1, right? And so, the binary number system is the reason why this works, right? And I'll show you in a second. Without going into it right now, and we'll go into it, the binary code for 16 right? Remember I told you, if you were to type in 16 in the computer, it would immediately change it to binary. Well, here's the binary code for 16. 1, 0, 0, 0, 0. Right? That's the binary code. 1, 0, 0, 0, 0. Ah, that's interesting. Is it really? Yeah.
It is.
Well,
I don't know why.
well, wait a minute. Wait a minute. All right, so that's a binary number for 16. 1, 0, 0, 0, 0. Remember, the first one we did was that one, right? Remember that? And remember it was 4, 2, 1. Remember that? Okay. And this was what? Whatever it was, right? Right? And remember we crossed out these two, right? Because those were evil, right? Are you following? The binary number for 9 is 1001. You see it yet? Okay. Just in case you don't see it, here's the key. The ones that are crossed out, the evil numbers are zeros. And the ones that remain are ones. Remain. The ones that are crossed out are zeros. Right? So, right off the bat, you know there's some relationship between the binary number system and this thing, right? Called Ethiopian math. Now, what's interesting about that? It's like, wait a minute. These guys are using the binary number system to do manipulation in the marketplace. Way before there was anything called a computer. Way before, they coined it the binary number system. So our ancestors were using this type of computation way before there were computers. That is cool. All right? And it turns out that this is Ethiopia specifically. It turns out that if you go all over Africa, there's something called fractal geometry. Fractal geometry that we use to lay out our villages and all that kind of stuff, and just all kinds of physics associated with it. And it's associated with the binary number system as well. And it's considered the math of nature, right? So we were working with nature, right? Laying out our village to work in concert with nature as opposed to working against it or opposing nature. All right. So this is Ethiopian math, the patterns associated with it, the link to the binary number system. Now we're going to go into the binary number system for real, right? So you see the link, yes?
Yeah.
Yeah, that's the pattern, and so that's real important. Now let's talk about the binary number system for a little bit, all right? And so what we're gonna do is we're gonna go from decimal, our number system, to binary, right? Because I told you that 1001 was 9, but you got to take my word for it because you know nothing about binary, right? Well, I'm about to share, right? And I don't like to say teach. I'm about to share what I know about binary so that you guys could check me, keep me honest, make sure that what I say, the binary code of something is actually what it is. All right, you ready? Let's do it. So, how you find the binary code or the binary number for one of our decimal numbers is that the first step in the process is that you write kind of like a tic-tac-toe grid like this, right?
Yeah, makes it double.
And so what happens is you put your decimal number here, right? You put the base here, right, which is base 2, right, because you're converting to binary, you're converting base 10 to base 2. Right? So 2 is the base that you're going to. The decimal number, pick a number. You want to do 9?
Yeah.
Just to keep me honest here, right? And then this guy here is the remainder.
Yeah.
Right? Remainder, when you divide 9 by 2, right? Or the decimal number by the base. All right, so you ready? Okay, so this column, remember, is remainder. This column is the decimal number, and this column is always the base. So, yeah, it's base 2, always going to be 2, right? All right, so what you do is 2 into 9 is what?
You mean 9 divided by 2?
Yeah, 2 into 9 or 9 divided by 2.
It's kind of like
It's 4.5.
division.
It's 4.5, right? Or 4 remainder 1. Right? Because it's,
Yeah.
right. 2 times 4 is 8, and then 1, 9, right? So 2 into 9 is 4, and remainder 1. Got it? Make sense? 2 into 9 is 4, and then remainder 1. All right. 2 into 4.
2.
2, and what kind of remainder?
0.
That is correct. All right? 2 into 2 is what?
1.
And what kind of remainder?
0.
All right. And so what you do, you don't need this, right? Because, you can't 2 into 1, can't do, right?
Right.
So you don't need that either. So what happened is that how you look at this is from bottom to top. So you look this way, right? So the binary number, the binary code for 9 is 1001. From bottom to top, 1001. As opposed to 1001. Got it?
Same up and down.
It is, but it's always from bottom to top. Because if this were not the same from both ways, right? Then you'd have something different,
New
On
binary.
the bottom than on the top.
right?
Okay.
And so to get you used to the process, the right process is you look from bottom, or you go from bottom to top. All right? So even though it looks the same, right? It's just because of the symmetry here, right? But you always go from bottom to top, and then you won't ever get it wrong. All right? So 9, like I told you, was 1001, right? From what we saw over there. All right. So that's 9. You understand this process,
Yeah.
all right? So let's pick another number.
Let's see, 105? Nah.
No, we're not going to do 105. We're going to do something
Easy.
something smaller, all right? Let's try 25?
Alright.
No, 25. 25 is good.
Maybe 20?
25?
25.
25 it is. All right. So 25 is the decimal number that we're looking at. All right? You remember what goes here?
The base number 2.
Base. All right. So that's 2, right? And the decimal number goes there, right?
And then that
And this is the
remainder.
remainder. Outstanding.
Did I answer one question?
All right. So we start the process. You ready?
Yeah.
All right. Let's rock and roll in. All right. So 2 into 25 is what?
12.
12. Any remainders?
1.
1. She was a different color. All right. And keep the base, right? 2 into 12 is what?
6.
6. Any remainders?
0.
0. All right. Let's do it again.
3.
Yes, 3.
That's 3. Any remainders?
No, no.
Okay, we'll do it again.
Yeah.
2 into 3 is what?
One.
Oh, yeah.
8 and it's 1.
One.
Oh.
And a what?
Remainder 1.
And a remainder 1. So this, right, the last one, you keep.
Oh, you're only supposed to look at the green ones. And
All right.
That's the
So-
binary code.
So the binary number for 25, that's the one in question, right, is 1, 1, 0, 0, 1.
Okay, one, zeros. Dad?
Yes, sir.
One question. Some people may get wrong by saying, going from the top to bottom. Like, sometimes they might get confused from going bottom.
I agree with you, right? I agree with you that, you know, it's natural, right? It's almost natural for us to go from top to bottom, right? Left to right, right? But as you well know, there's a lot of cultures that go from right to left, right? In this case, we go from bottom to top, all right? So it's 1. So the binary number for, so yeah, I could put the base down at the bottom. So that's base 10, 25 and base 10, right? Equals 1, 1, 0, 0, 1, base 2. So that's how you write that. All right? And it's different than 1, 0, 0, 1, 1. That wouldn't be right. All right? And you got to take my word for it again, right? Because you don't know how to convert from binary to decimal,
No.
right? I just showed you how to convert from decimal to binary. But guess what? I'm going to show you. Because I love you. All right. So everybody got that? All right. So that's what the computer does immediately. As soon as you put that 25 in, it changes it to the binary equivalent, right? And then manipulates it. Does all that it needs to do with those 1s and 0s, and then it converts it back to, you know, what we're used to seeing, right? All right, so we're gonna go do. We did from our conversion from decimal to binary. We did that. Check. All right. Let's do from binary to decimal. All right. This is gonna be fun. All right. Check it out.
This better be.
Let's think back to kindergarten. Kindergarten, all right? Kindergarten, remember place value? Place value. All right. If you had 123, right? This was the 1s. This was the 10s. And this was the 100.
Hundreds. Oh.
Remember that? Okay. And if there was something here like 4, it would be what?
1,000.
That's right.
I learned that in 2nd grade.
All right. And if there was something here,
10,000.
exactly, right?
And then all of a sudden be 100,000 instead be a millions.
Right? And if there, and so
Oh.
that's how that was, right? In kindergarten. But what they didn't teach you in kindergarten, what they were getting you ready for is this today. All right, here we go. this is actually, ones is actually 10 to the 0 power, right? This is the base, 10, right? And this is the place, so it's 10 to the 0 power is 1. Now, here's the thing. Anything to the 0 power
It's always one.
is always 1. So 4 to the 0 power is 1. 100 to the 0 power is 1. 524 to the 0 power is 1. Now, what is that? 0 to the 0 power. Now 0 to the 0 power is a trick question, right? What happened is that 0 to any power is 0,
Oh.
right? Because anything to some power is that thing times that thing times that thing, right? 3 times. 1, 2, 3. So it's that same thing multiplied by itself 3 times, right? Third power. If it was 4, it would be 4 of them, all right? So if this is 0 to the third power, it would be 0 times 0 times 0. And 0 times 0 times 0 is 0, right? So 0 to any power is 0. But I just told you that anything to the 0 power is 1. So 0 to the 0 power is 1 or 0.
0.
This is called indeterminate. It's an indeterminate form.
I've actually heard of that before.
It's indeterminate form, right? So because there are 2 conflicting rules, right? 2 conflicting rules, we call it indeterminate, okay? And so typically when you see this form, and you'll see it in calculus and all that kind of stuff, when you see it, it means that you have to look deeper to really understand what's going on. You got to look deeper, all right? And actually, one of the things that I should have done first, when I get to talk to new people, is this exercise that I'm going to do. So forget this for 1 second, and let's do the exercise that I should have done initially, all right? Whenever I start talking to new people, all right? And here's the exercise, all right? So we're going to get back to this, but here, this is very important. What is this? What do you see?
Figure 8.
Okay, you see the figure 8.
I see an 8 only.
All right. You see anything? What do you see?
2 0.
2 zeros. I like it. 2 zeros.
See,
2 zeros. All right. 2 zeros. All right. You see anything?
Infinity sign.
The infinity sign. I like that. Infinity, 90-degree rotation. Yep. 90 degrees. All right.
That's the infinity sign?
Yep. That's what it looks like. Infinity. You see anything?
No. Only see what.
How about this? How about this? I'll tell you what I see. I see 4 plus 4. That's what I see. See anything? 8 times 1? Right? How about 8 plus 0? Right? How about a racetrack?
That's what a racetrack looks like.
Yeah, there's a racetrack that looks like that. Right? How about, I don't know, 6 plus 2? Right? How about 10
Nice.
minus 2? Right? Right? So what the point here is that we have to see all these things, right? Just by looking at this, right? So whatever is appropriate at the time we need to see, then we got to see that. Do you understand? So there's no singular answer. It's all relative. right? And it's interesting because the only thing that's absolute is what? That everything is relative, which is kind of interesting. That's a paradox, right? All right, so let's get back to this, right? So now that you can see a little bit better,
How long is your class gonna be? Cause I gotta shoot over there for a second
it's gonna be till 3.
to 3.
Yeah.
Okay. Well, I might be back, but I came for that 2 o'clock thing they were having over there.
Okay, okay.
I was
All
just
right.
stopping through.
Well, let me just
Yeah.
show you this real quick,
Okay.
and then, you know, you could go. We'll be almost over. All right. So here we go. Place value, base 10, right? Kindergarten. This place here is called the ones, and I just showed you why it's called the ones, because 10 to the 0 is 1, right? Well, here's the next place is actually 10 to the first power. Anything to the first power is itself, right? So 10 to the first power is 10. That's why this is the tens, right? All right. 10 to this place is 10 to the second power, which is what? 10 times 10, right? Because anything to the second power is itself, you know, it times itself, right? Twice. So it's just 10 times 10. 10 times 10 is what?
100.
Right. And that's why that's the hundredths place.
Oh, now it starts
Right?
going
Ah.
really good.
Now this is 10 to the third power, right? Which is 10 times 10 times 10,
Here's 1,000.
which is 1,000, right?
Yeah.
And so this is the,
Thousands place.
right.
Now for
So this is
ten.
why they teach you just to add a 0 when you're young, when you're doing multiplication.
Well, kind of, sort of.
Yeah,
right?
because ones you have no
Kind of
zero.
fun.
Tens
Right?
you have a 0. 100 you have two
So-
zeros.
So because of adding that 0, we know that 10 times 10 times 10 is 1,000, right? Because you just add the zeros, all right? But in terms of place value, right, you put it here, would be what? 10 to the 4th power. The next place would be 10 to the 5th power, and all that kind of stuff. Now, what does this have to do with binary?
It's all
Right.
ones and zeros.
All ones and zeros, right? Here's the thing. If I gave you a binary number, 1, 0, 1, something like that, right? What happens is that it's very much like this, right? The base is 2 instead of 10. This is 2 to 0. This is 2 to the 1, 2 to 2, 2 to the 3, 2
Also
to the
that
4, 2 to the 5, and 2 to
Okay.
the 6. Right? So each one of these places is that. Right? And so how you got to look at it, right? What is 2 to 0? We said what it is.
1,
2 to the first power,
2,
2 to the second power,
4,
2 to the third power.
8,
Outstanding. And then what?
16,
Okay,
32.
okay,
64.
okay, pretty good, right? All right, so now, right, think of the ones as yeses and think of the zeros as nos. Yes and no. And so, here's the question. The question is, should I add 1?
yes,
Yes. Should I add 2?
no,
Should I add 4?
yes,
Should I add 8?
yes,
Should I add 16?
yes,
Should I add 32?
no,
Should I add 64?
yes.
Okay, so, see? Plus, right? Plus, this is a no. Plus 16. Plus 8. Plus 4. Plus, that's 0, right? That's a no, plus 1, right? So now all you gotta do is add them up, and you got it. And it's just like this, which is really what you were doing, is you know, adding 4,000 to what's this? 100, right? And you'd add 20, and you'd add 3. So it's 4,123. Well, this is 64 and 16 what? Right? 80, right? And then this is what? 88, and then this is what?
92,
And then this is what?
93.
Right? So this here is the binary number for 93. How cool is that?
That's cool.
Yeah. Right? So, see, our ancestors had to know all this to be able to come up with the initial pattern, the initial process for the Ethiopian math. How cool is that? Right? So here's the thing. When people talk about oh, Africans discovered math and all this kind of stuff, typically they're just saying it and don't actually have an example of it. You know what I mean? That they could show people, to prove to people. Right? You could point to the pyramids, but do we know the math that goes into the pyramid, that went into the pyramids? Most of us don't. Right? And so this Ethiopian math, right, and the fact that it's linked to the binary number system, and binary number system is what they used to develop the computer system that we use now, right? And they will take credit for something that that they learned from us. You can call it stealing if you want to, but they learned it from us, is the point, right?
Right.
Thank you, sis.
Thank you, I appreciate it. You gonna be back next Saturday?
Not next Saturday, 2 Saturdays from
Oh, wow.
yeah.
I
All
guess
right.
I get another email or something.
Yeah, absolutely.
Okay,
All
well,
right.
appreciate it. That's
No
what I'm
problem.
talking about.
That
Yes, sir.
is there any number you cannot put in binary base 2?
No. All numbers in base 10 can go into base 2. Could be converted. All right?
No one.
Go ahead.
That is in binary, is there two numbers or is that that when you convert them they both equal the same thing?
No.
Okay.
Just like, are there any two numbers in the decimal number system that are the same? No. Right. Okay? Right. So that is the binary number system in a nutshell, right? You know how to convert from the decimal number system, which is now our number system, to the binary number system, which is the computer number system, right? And then you know how to go from the computer number system, which is the binary number system, to our number system, the decimal number system. Right? And what's really cool is that we could actually develop, us four right here, could develop a number system, for ourselves, base 6. Develop a whole number system, base 6, and develop a computer, build a computer that uses base 6, and it might be faster or slower or different or whatever than the current computers that are use base 2 and our number system that we currently use, which is base 10. And so the point is that we're not locked into any one number system or any one way of looking at things, right? You could have a greater appreciation for different cultures and different people and different perspectives if you understand that, differences are a good thing, right? When we're working together for the betterment of humanity, right, then differences is a good thing, right? But if you're working to destroy humanity, then, you could turn anything bad. Yes, sir.
One thing I was gonna say, the only two bases you cannot really create are base 0 and base 1, really.
Why can't you?
Because base 1 would be only zeros.
That's a good point. That's a very good point. All right. So there you have it.
Also, when you convert it, you kind of divide it into 1, which 1 divided by let's say five equals 5, and then you'd have to go
You mean
on
five?
and on and on and on.
5 divided by 1.
Yeah.
Okay.
Which then you'd have to go on and on and on.
You're absolutely right. Right? Well, just repeat the same thing. Go
Yeah.
ahead.
How many bases are there?
How many bases? An infinite number.
Infinite,
Yeah,
which is infinity.
absolutely. Right? I
Except-
mean, you could come up with a base 101. You could come up with a base 102. You could come up with a base whatever. Do you understand? Right?
Not a base.
Now you just gotta figure out the application, right? You can't just do stuff to do stuff. How can you apply it to again make humanity better? Do you understand? Right? And in this case, we're talking about the binary number system, which is a computer number system, a computer language, if you will, right? That's the language that the computer speaks. And so, if you think of it that way, if we use computers to get smarter, to cure cancer, right? To prevent cancer, right? And we always prevent cancer, we never need to enact that cure, right? Because nobody will have cancer permanently, forever, right? And I mean, we'll be doing something else and stop researching about cancer and spending all this money and walking and flying and running and riding for cancer, right? So we would be eliminating all the problems in society, right? Using the computer and our intelligence that is gained from using the computer. All that from the binary number system. How cool is that?
Good.
Exactly. Right? And so the point is that everything that we know, everything that we come up with, we should be using for the betterment of humanity. All right? So the next thing that I want to do is I want to make absolutely positively sure that you guys understand. All right?
Okay.
So this is what we're going to do. It's quiz time. Ta-ta-ta.
Okay, this is gonna be hard.
All right,
It's a
all right,
tough
all right,
one.
all right, all right. So, I'm going to put up a decimal number. Right? And, you know, raise a hand. You know, just somebody raise your hand. I acknowledge you. You tell me how to change this decimal number to a binary number. Right? Just walk me through the process. All right? All right. So, number 8. Anybody want to? We're going to convert 8 to, this is base 10. We're going to convert it to binary, base 2. That's a question mark. All right? What's the first thing we do?
How many times does 2 go in that game?
Is that how you do it? What's the first thing we do when we're going from decimal to binary? Remember?
I agree.
Yeah. You got to do that tic-tac-toe grid type thing, right? It's about the process, right? That way we get it right every time, right? And so we put the decimal number here, remember?
The base to the right,
The base here,
which is 2,
base 2,
and a remainder.
and the remainder here.
Okay, so.
All right. So now we could go 2 into 4, 2 into 8,
4. No remainder.
0. All right, 2 into
2.
2 into 4,
5.
2 times,
No remainder.
0 remainder,
2 and a 2 goes once. No
Once.
remainder.
no remainder. So what's the binary number for?
1,
For
0, 0,
8.
0.
Good. Right. So this is 1, 0, 0, 0.
That's the same thing as 1,000, but
Right?
actually
And
in just
no, this is not 1,000.
I know, but in the
No.
first place, people would just think it's 1,000.
Well, and that's interesting that you would say that, because now, if I asked you, now that you guys know what you know, if I asked you what number this is, what would you say?
1, 1.
Ah, you said 1, 1, right? And you said 11, right? See, this is 2 to the 0 and 2 to the 1, right? Which is 1 and 2, right? So do you add 1?
No.
Yes.
Oh, okay.
No, this
No,
is number.
add those.
So
It's
yes,
not
right? So
the
you add
top.
1. Do you add 2? Yes,
Uh,
right? So that's 3. So this is actually if the binary number for the decimal number 3 or 11 in the decimal system, right? So that's why if I ask you what this is, right? Your next obvious question should be, what number system are you asking? All right? Because if it's in the binary number system, it will be number 3, right?
In the
In
decimal,
our
it would be 11.
and in the decimal number system, it would be 11, right? So that's why when you say this is 1,000, right? If I just write this, you wouldn't be able to tell if it's 1,000 or 8,
It's
right? And so, you know, I would have to ask you. That's why I put the little bases down at the bottom to tell you that I'm talking about base 2 here. I'm talking about base 10 here. All right. So you got that, right? And now we could check our answer, right? Right? Because look, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, right? So that's 1, that's 2, that's 4, and that's 8, right? And so this is no, right? No, no, yes, right? So do I add 1? Did I add 1? No, right? So no. Do I add the 2?
No.
No. Do I add the
wait a second. They
4?
already have the
No.
answer.
No. Do I add the 8?
Yes.
Yes, and that's the answer.
Got it?
You guys already
Alright,
have
so
the
it's
answer.
it's 8. So you know, that's how you check it. Right? So you just think of the binary code as yeses and nos. The 1s are yeses, the 0s are nos, right? It's kind of like the evens and odds, right? The evils and the goods, right? All right, so we've just proven that we know how to go from decimal number system to the binary number system, and we checked it, right, by going from the binary number system to the decimal number system. So I fully
Taught
agree
us.
that you guys know how to do that. So do you feel a little bit better?
Yes.
Okay, now what's interesting is that I learned the decimal number system during the second year of engineering school in college. Second year, engineering school, right? And you guys are in what? What grade are you guys in?
We're in
You go to
I'm-
second grade,
4th.
and you're in 4th grade, and now you know the binary number system. How cool is that?
Yeah,
So
it is.
it's quite simple enough. It's simple enough for you to learn as a second grader,
Yeah.
as a 5th grader,
As
Right?
a 5th grade. Wait a second.
as
And
a,
now-
as a 4th grader, as a 3rd grader. You could
Yeah.
learn it. That's the point, right?
Yeah,
And
I
so
can
you
learn
really
it.
don't have to be in engineering school to learn the language or the number system that computer uses, right? And so that's another reason why the Ethiopian, the Africans, right, us, used it and actually still using it over in Ethiopia in the marketplace. It's quick and it's easy, right? And we could do things like, you know, if it's 32 that we're using to figure out, you know, a product, we just double it 5 times and we're done, right? So all you gotta learn is doubling, you know. All right, so last thing we're gonna do is make absolutely sure that you understand the process for Ethiopian math. All right. Got it?
We are.
So,
It's just testing us out again.
all right.
155.
155. Wow.
7 times
200.
13.
Oh.
Yeah. Do you know what it is?
No, but I
Neither,
can't grasp it.
neither do I. I don't know what it is, right? But
Well,
we're gonna
let's
do
use
it.
the
How cool is
binary.
that? Let's do it.
Yeah,
All right.
let's just
So
do it.
let's just do it. All right. All right. Ready?
I could figure it out in my head, but I'm not going to. I was
Now
like,
we're
okay.
using this process. Let's use the process, okay? All right. So remember what we do with this one?
Half that,
Half it,
double that.
double this one, right? And be,
Okay.
so what do we get?
3.5.
Do we need the 0.5?
No.
No.
Okay, so we toss the 0.5, right?
Mhm.
Half this is what?
1.
1.
Right? Toss that 0.5 again, right? So we're good there. What's this one?
Oh, this one.
Double it.
26.
Double.
26.
26. Okay, that's what she said. I thought you said 6. I was like, all right. So 26. You double it again, right?
42.
So it's 42.
42.
Oh, wait a second.
Look
It's
again.
52.
Okay.
52, I'm sorry.
I
52.
can't believe I got it wrong in the first place.
All right, 52. All right. Now we cross out the evens on this side, right?
Mm-hmm. You have
What-
that.
No
We have
evens.
none. So what do we do?
You
All
add
of them
those up.
combined.
You just add them, right? So this is what? 9,
Yeah, that's 9.
11.
11. Add
Right?
1.
What's that? 4 and 5.
That's 9.
91. Anybody want to check?
Alright. 13 times 7, 7 times 1 is 21, 1, 2, 91.
Isn't that something? It works every time, right? Now, here is the not $1 million question.
Oh, man. Okay, this is good.
Let's see. It's not dollars. We don't use dollars in here,
No.
right? Because I'm king in here, right? And so we don't use dollars. What we use is humanities.
What are humanities?
Ah, good question. I was hoping that somebody would ask what humanities are. If I were the ruler of this planet and everybody had to follow my rules, right? What I would do is say, okay, we're going to change the currency and we're going to use humanities, right? Humanities. And this is what humanities are. We're going to throw out dollars and pesos and all that kind of stuff. We're going to use humanities. Humanities is a currency that the more humane you are, right? The more humane you are is the more humanities you get. So if you help your brother and your sister, right? If you help to feed them, if you help to educate them, if you help to solve whatever problems they have, you get humanities. Right? You solve world hunger, humanities. You'll be rich with humanities. Right? And so the richer you are with humanities is the more, that you could do for humanity. How cool is that? So if you are poisoning the earth and the water supply and all that kind of stuff, you've got to pay humanities. You get taken away from you because you're not being humane. All right? So the million humanities question is, what's the binary number or binary code for 7? Da, da, da.
Time to
No, wait a minute.
convert.
By looking at this, remember, the first thing that we did was we made a correlation between the binary number system and Ethiopian math. We just did Ethiopian math. So by looking at this, you should know what the binary code for 7 is.
1.
111.
111. Right? Because we didn't cross out anything, remember? All the rows that are crossed out?
Yeah.
0.
So that means
Right?
the 0. So that means
That's one,
the-
one, one.
The sides, well, that means you have on the left side, if any of them are odd, well, all of them are odd, really, so it's a 1. So
That's
odd.
exactly right.
And then if you had, let's say that was that, let's say that one was 8. Let's do it different. That 7 was changed into an 8, and then you had the 4. That means those two would be crossed
That is
out.
correct.
Then you'd have a little bit more than the column you'd have.
Well,
So-
you'd have some zeros in there. You
Yeah,
wouldn't
you'd
just have all ones,
one,
right?
one,
You'd have to cross out the rows, all right? Because those rows would have even numbers or evil numbers in the left column, all right? All right, so, you got that? All right? That's all I got. We've done Ethiopian math. You understand the process. We've seen that our ancestors, right, us, Africans, we've been using the binary number system to do computation, to calculate some stuff, right? You now know how to go from the decimal number system to the binary number system, and from the binary number system to the decimal number system, right? So you have a better appreciation for the type of stuff that the computer does. So if you were to go into like a computer science or a computer class where you're talking about assembly language, which is where the computer, registers where you actually change ones and zeros, if you were to go into something like that, you'd have a better understanding and you'd be able to track it better. Yeah. And learn all the stuff that they're teaching better because you have a better understanding of binary. And not only that, you'll feel your connection to it because your ancestors, were using it way before there were computers and the so-called binary number system, as it's called. All right? So, that's all I got. Thank you for your time. Thank you. You're too kind. All right? All right.
That was good, Dad.
Thank you, Tafari.
You're welcome.